Question 5.6. Now, this was a bit of a cheeky one because I gave you a question in last week's workshop on linear equations to do with brain weight for brain mass. And actually, that I didn't say it in the question, but it was for mammals, I think. And I told you to plot brain weight on the Y and body mass or body weight on the X. And you did that in good faith. Thank you. But it looked a bit shit, didn't it? Right? There's a lot of scatter in it. This is what it looked like if I zoom in a bit there. So you had brain weight on the Y. I should have labeled my axis. That's very, very naughty. I should have labeled my axis there. But brain weight is on the Y and body weight is on the X. Okay. And I asked you to plot a trend line. So you did that in Excel or Google Sheets. And you got the parameters of that linear equation out. So you got the gradient and the line of intercept. And then I think I asked you to calculate the brain weight of something which weighed 50 kilos. Okay. And you would have given me an answer which would have been on that line. Okay. Okay. But what if applying a linear fit to this wasn't appropriate? Okay, what if there was some other model that I could apply to it? So what this question is getting you to do, let me read the question. I've said perhaps using a linear function to describe the relationship between body and brain weights was not ideal. What happens if you plot the log of brain weight versus the log of body weight? And when I say log, I mean log to the base 10. So shall we do that? How do we do that? Well, let's go back, and I've got some more columns here. So there was the original data. Oh, it's going to be funny. Hang on, give me a second. Let's get rid of that. Let's do that. I don't know where my original data's gone, but in your original sheet, firstly, you converted from pounds to kilograms. So if you've done that already, great. If you haven't, convert your body weight column and your brain weight column from pounds to kilograms, and then I'm going to take the log of each of those columns. Right? And if you do that in a spreadsheet, I can show you if my fingers are good enough. Right, so down at the bottom here, I simply, this is really hard to do on an iPad. Hang on, zoom in a bit. That looks a bit better. Right, there you go. Right, so I've got body weight in kilos, brain weight in kilos, and then I've done the log of the body, and it's difficult to see, but down the bottom here, I've done equals log 10, open bracket, and I put in the cell reference that I need. In this case, it's the body weight I'm doing, so I'm going to do E2, and then I'm going to copy that down, just pull it down, and it should do it for the whole column. I'm then going to do it for the brain weight as well. So this time I've done F2, and I've copied that down. Then I've highlighted both of those columns, the logged columns, and I've made another scatter plot, which looks like this. And now, I hope you will agree that that looks much more like a linear fit. Okay, so the original fit between direct fit between brain and body wasn't great, really, but the linear fit between the logs of both of those columns is much better. And now, if I take and if I add a linear trend line onto this, I can actually extract the gradient and the intercept of that line, which will be different, very different from the original values I extracted without taking logs. Okay, so you should do that, and you should get these values. So I've got let's have a look. Yeah, it's difficult to see here. If I zoom in, can I zoom in? No. I've got a value for the gradient of 1.18 and a value for the intercept of -1.01. Okay, so let me just do this. Let me go back to my notebook and do the rest of the question on paper. Right, so I basically just done this. Actually, it was kind of like that. It had, let me draw it again. okay, where this was the log of the brain weight, let's call that log B, and this was the log of the body mass. Okay, and I have extracted a line of best fit of y equals mx plus c, where m is equal to 1.18 and c is equal to minus 1.01. Let's write that equation out explicitly. Okay, I'm going to do it in red because that's how important it is. Y is not just the brain weight, it's the log of the brain weight. Okay, so you have to write that in. Log B is equal to a gradient of 1.18 times the log of the mass, log of the body mass, log, I called it big M, minus 1.01. Okay, and I've asked you to write it in the form, rewrite this in the form B is equal to A to the big M, that's the body mass, and then little m here, okay? Now, that is another type of equation, relationship, which Andy may have touched upon in his lecture, called a power law. Okay, so it's not a straight line, certainly not a straight line. It's also not an exponential function because there's no exponential term in there. But if I was to actually plot my original graph, okay, and instead of logging it, it was something like this. It was all scattered all over the place. Instead of being a straight line, the power law will probably look something like this. Okay, and that is actually a better fit to that data rather than a linear fit. So we've taken the logs, we've got this out. How do I rewrite this in a power law form? Right, so there's something I want to do first. I'm going to get rid of this. It's a bit of a mess, isn't it? Let's get rid of that. Okay, so this I'm going to go really slow because it's, again, all it is logarithmic algebra, but we're actually going to go kind of backwards to some of the examples I showed you earlier on. I'm thinking about question 5.2, right? So I want to go from some expression which has logs to one without logs, okay? And to do that, I'm going to need to worry about this term first, the minus 1.01, because what I would really like is for every single term in my equation to have logs. That is going to increase the chance that I can get rid of a log term, is if every term in my equation has a log in it, right? So I'm just going to say, to begin with, that this is going to be log C, okay? Actually, I think I called it log A. Let's call it log A. Okay, so log A is equal to minus 1.01. That's perfectly okay. I can define a new algebraic term as something and then substitute it in. Okay, so let me rewrite this equation now. Log of B is equal to 1.18 log big M plus log of A, provided that a log of A is equal to minus 1.01. Okay, right. What else can I do with this equation, right? What other rules can I throw at it? Well, I would like to combine these two, but I can't because I've got a factor here. But I know another rule that means I could take this up to the index of the big M. Let's do that. Log B is equal to log big M to the power 1.18. Totally fine. Still got this log A term. Okay. And now it's totally legit if I want to combine these using my summation rule, my additive rule. Okay. Because that's just a log B is equal to the log M 1.18 times by A. Okay. Now I'm there. I've got a log there, and I've basically logged both sides of that equation. okay, with no other sort of factors or anything hanging around, which means I can write it without the logs as well. I'm going to write this in green. B is equal to, I'm going to swap these around. So that's A m to the 1.18, okay? So in this case, that little m is 1.18. Remember the form I was trying to write it in? And I've already said A is equal to well, log A is equal to minus 1.18, so A is equal to 10 to the minus 1.01. Okay, so that's how you do it. Okay, so it's not a linear function that best describes that relationship. It's actually a power law with those parameters.